All right, so we're going to do the first sample problem uh, dealing with this change in energy. This is Nelson Physics old textbook, sample problem number 1, page 286. Okay, and the question is as follows. The question is, what is the change in the Earth's gravitational potential energy for an astronaut of mass 64.5 kilograms lifted from the Earth's surface into a circular orbit of altitude? So altitude is 440 kilometers. Okay, now just a few things that we want to clarify before we go any further. First things first, when we are talking about R in this chapter, that R is RE plus R altitude. RE is the radius of Earth from the center of Earth to the surface, and altitude is your height above the surface of the Earth. Okay, so from now on, whenever we talk about R, that's what we mean. We mean R is RE plus R altitude, and all of it has to be in meters. Yes? Well, what? I just explained it to you. I just explained this to you right now. 6 plus, this is going to be, and you got to convert this into meters, 440,000 meters. Okay, 440 kilometers, convert this into meters. Okay, and you end up with R as being 6.82 times 10 to the 6 meters. So as I said, when I'm talking about R from now on, we mean RE plus R altitude. Altitude is the height above the surface of the Earth. Above surface of Earth. Just be aware that you are reading the question properly. Sometimes they tell you the orbit is 450 kilometers above the surface. Or they will say the orbit is 450 kilometers. And when I say 450 kilometers, it means from the surface. Okay? So that's something that you need to be aware of when you are answering these questions. So what we're going to do here is the first thing we're going to do is we're going to, of course, write down our unknowns and our givens, which is mass of Earth 5.98 times 10 to the 24 kg. R, which is 6.82 times 10 to the 6 meters. Okay? The first thing we're going to do is we're going to figure out what my EG is on the surface of the planet, which we said is our maximum. EG on the surface. Okay? And this EG right here is EG1. And we're going to say EG1, and remember our formula, is negative big G, big M, M over RE, because we're on the surface, so that's why it's RE. Okay? Plug our numbers in, 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24 times 64.5. Now this is just for an astronaut of that mass. We're not even talking about the space shuttle yet. We're not talking about any spacecraft. We're just talking about to bring that much of a mass, to raise it 440 kilometers above the surface of Earth. How much energy do I require? Now remember, one of the mistakes that you're going to make, very straightforward mistakes that people make, is when they do this, they confuse FG and EG. FG is R squared, EG is R. So do not confuse the two. There is no R squared here. Okay, it's just R. And when we're doing this right here is going to be 6.38 times 10 to the 6 meters. And please, can somebody give me what the value is? What is the answer? What is EG1? Okay, so 4.03 times 10 to the 9 joules. We're talking about billions of joules of energy. Okay? All right. Now that's just for the astronaut. Yes. Negatives right here. Good boy. Yes, negative every time. So this is my second EG2. This is when I am in orbit, and that is 6.82 times 10 to the 6 meters. Again, remember this is not squared. And what do you get for EG2? Again, it's a negative answer. So negative 3.77 times 10 to the 9 joules of energy. Okay? Okay, we're not done the question yet. We were asking what is the energy required to put this astronaut into space. So now what I need to do is subtract the two. And then for some of you who had that question as to why was one a positive answer and one was negative, there is my change in energy, which is EG2 minus EG1. EG2 being negative 3.77 times 10 to the 9 joules of energy minus negative 4.03 times 10 to the 9 joules of energy. Now remember, that's what our formula said, right? Our formula said EG2 equals to EG2 minus EG1, which was negative minus negative. So what do you end up with in terms of change in energy? What is your answer? Of course, it's going to be a positive answer because that and that is going to be a positive. So what is your change in energy? How much? So 2.6 times 10 to the power of 8 joules. Look at that. Positive answer. This is how much energy will be required to put an astronaut from the surface of the Earth to 400 kilometers above the surface of the Earth. That's just one astronaut. It's a lot of fuel. It's a lot of energy. But you see how now it became positive? That we're not talking about anything else, just the astronaut. Are we good? Yes? Nuja? Why is it negative? Okay, yes. Yeah. We said that the maximum EG will be on the surface. Yes. We're not talking about, but because all the time our energy is always talking about it from the center of Earth. We've always talked about it from the center of Earth.
So essentially we're looking at the difference between the energy from, like the total energy from the center of the Earth to the orbit minus the energy of just the center of the circle.
No. What we're saying is that we know that for force, the further away you are from the surface, the less gravity there is. Right? So if I'm closest to the surface, my gravity is maximum. So therefore my gravitational potential energy is also maximum at the surface of Earth. And since gravity is always thought about as at the center of mass of any object. And the center of mass of Earth is the center of Earth. Right? Alright, so that's that with this one. We will continue with the next section of this chapter tomorrow, where we change this up slightly. This is one way of doing the question, and all we're talking about here is changing energy from the surface to orbit. We're not talking about anything else here. So tomorrow we'll change it up slightly, and we'll talk about it in a different way. And so it's going to be an interesting chapter, this chapter is. Okay? So far so good? Okay. Look at it, let it sink in. I know it's, yeah.